Soldering is one of the oldest known methods for joining two pieces of metal together, and is done by melting a compound of the soft metals tin and lead, called solder, into the gap between the metal pieces to be joined. Solder comes in a variety of shapes and alloys. The 1-pound spool of wire solder is the most familiar form of solder and is available in several wire sizes or diameters. It can be had as a solid wire, an acid cord wire, a rosin cord wire. Rosin cord wire is the most widely used solder for electronics work. Bar solder is available in a number of alloys and is used for many large work applications. Preformed solder in specially designed shapes is made for solving a wide variety of unique and difficult soldering jobs. Solder is created by combining the soft metals tin and lead. The proportions of tin and lead in solder vary depending on the job to be done. When the proportions of tin and lead are equal, the solder is known as 50-50 solder. 60-40 solder would consist of 60% tin and 40% lead. 63-37 solder would consist of 63% tin and 37% lead. The chemical symbol for tin is SN. SN63 indicates a solder which is 63% tin. One of the unique things about solder is its low melting point. And even that varies as the proportions of tin and lead are changed. Pure tin has a melting point of 450 degrees Fahrenheit. Pure lead has a melting point of 621 degrees Fahrenheit. When tin and lead are combined to make solder, the melting point changes. For 50-50 solder, the melting point drops to 420 degrees Fahrenheit, lower than either of the two metals alone. With most combinations, melting does not take place all at once. 50-50 solder begins to melt at 361 degrees Fahrenheit, but it is not fully molten or liquid until the temperature reaches 420 degrees Fahrenheit. Between the time the solder begins to melt at 361 degrees and the time it becomes fully molten at 420 degrees Fahrenheit, the solder exists in a plastic or semi-liquid state. Some of it, but not all of it, has melted. A slight movement of any element of the joint during this cool down or plastic period after the soldering iron has been removed may cause what is known as a disturbed joint. Such a joint is unreliable and unacceptable in high reliability soldering. The plastic or semi-liquid range of solder varies depending upon the tin to lead ratio. A special example is the 63-37 ratio, or SN63, known as eutectic solder, more generally referred to as SN63. This combination has practically no plastic range, or in other words, it melts almost instantly at 361 degrees Fahrenheit and solidifies almost as fast when the soldering iron is removed from the joint. SN63 is the recommended solder for use in electronic circuit board soldering, where use of minimal heat is necessary to avoid damaging heat-sensitive components. In any kind of soldering, the primary requirement beyond the solder itself is heat. Soldering irons are the instruments used for conveniently generating and storing the necessary heat, and the major consideration in the choice of the type and size of a soldering iron is the problem of controlling the heat cycle of the work. How fast the work gets hot, how hot it gets, and how long it stays hot. Soldering irons come in a variety of sizes, shapes, and wattages, but consist basically of three main elements. 1. A resistance heating element. 2. The heater block, which acts as a heat reservoir. And 3. The tip or bit that transfers the heat to the work. The resistance coil, which is wrapped around the metal core of the block, generates the heat needed for the soldering process. The block and the soldering tip store the heat created by the coil and are referred to as the reservoir. The tip is the pipeline through which the heat flows into the work. The soldering tip is removable and comes in various shapes and sizes. For small work, a neck-down tip is used so that only a small amount of heat flows. For large work, a large tip is used to provide a greater heat flow. And the larger the heat flow, the greater the drain on the reservoir. It is important that the heating block be large enough to provide heat to the reservoir faster than the tip can deliver heat to the work. An iron's capacity, or the ability to deliver heat to the reservoir faster than the tip can transfer the heat to the work, can be increased by using a larger heating element. And increasing the capacity of the heating element is done by increasing the wattage of the iron. These two factors, block size and wattage, determine the iron's heat recovery rate. The first factor to be considered in the making of a reliable solder connection is the thermal mass of the joint, the amount of metal in the joint. This mass may vary over a wide range. For example, there is relatively little mass in a single pad on a single-sided circuit board, so the pad heats up quickly. If the circuit board is double-sided with plated through holes, the mass has more than doubled and will take longer to heat up. Since all components are not the same size, component leads will also increase the thermal mass of the joint, and in varying amounts. There may be bifurcated or turret terminals mounted at the joint which will increase the mass, and the mass will increase still more as one or two connecting wires are added. Each joint has its own particular thermal mass, and how this combined mass compares with the mass of the soldering iron determines the time and temperature rise of the work. With a large work mass and a small iron tip, temperature rise will be slow. With a small work mass and a large iron tip, temperature rise will be rapid, even though the temperature of the iron tips is the same. To reliably solder a particular joint, you need a soldering iron that provides the right temperature, has the correct size tip, has a heat capacity equal to the demand of the thermal mass of the solder joint being made, has high heat recovery rate. The second important factor in the making of a reliable solder connection is the surface condition of the metal of the joint. The first time the soldering process is seen, it might appear that the solder simply sticks the metal pieces together like some hot melt glue. What actually happens is far different. Before a reliable solder joint can be made, the metal surface must be truly clean. It must be free of oil, grease, and other contaminants. It must be free of the oxide films that occur when metal is exposed to air. Before attempting to solder any joint, the work should always be wiped clean with a solvent such as isopropyl alcohol to remove grease and oil from the surface. While the cleaning of the metal surfaces with solvent is essential to a reliable solder joint, a solvent alone will not do the complete job because of the fact that when a metal is exposed to air, an oxide film forms on that surface. When metal is heated, as in soldering, the oxide film thickens extremely rapidly. thus creating a barrier which prevents the solder from coming into contact with the metal surface. The solder acts like water on an oily surface. No wetting action takes place, and the solder can be easily scraped off. For a good solder bond, surface oxides must be removed during the soldering process. To remove oxides and keep them removed during the soldering operation, a natural or synthetic rosin called flux is carried to the work surface as a core in the strand of solder. Flux melts at a lower temperature than solder, and so starts the corrosive fluxing action of removing the oxides and preventing the reformation of new oxides before the solder is fully liquid. As the hot solder comes into contact with the copper surface, a metal solvent action takes place. The copper dissolves and the solder penetrates the surface. The molecules of solder and copper blend together to form a new metal alloy. A metal that's part solder and part copper, with characteristics all its own. The solvent action is called wetting and forms an intermetallic bond between the parts. The third important factor to be considered in the making of a reliable solder connection is thermal transfer, the amount of heat transferred from the tip of the iron to the joint allowed by the area of contact. As you can see, the area of contact between the tip of the iron and a round lead is very small. The contact area can be greatly increased by applying a small amount of solder to the point of contact between the tip and the workpiece. This solder bridge provides a larger area of contact and assures the rapid transfer of heat to the joint. The fourth and critical factor to be considered in the making of a reliable solder connection is time. The general rule is, for high reliability soldering on printed circuit boards, apply heat for only the time needed to complete the junction. 2 seconds for thin double-sided boards, up to 5 seconds for thicker multi-layer boards. Keeping the hot iron on the joint longer than these recommended times may begin to damage the circuit board. The secret to good soldering is learning to recognize the rate at which heat is flowing into the joint. This means observing how fast the solder melts, which should be within 1 to 5 seconds. If the tip of the iron is too small for the work, it will produce a mush kind of melt. The heating rate will be too slow. If the tip of the iron is too large for the work and too hot, the heating rate will be so fast that it can't be controlled. A good rule for preventing overheating is to get in and get out as fast as you can when you see a good connection has been made. The purpose of the soldering procedure is to join two pieces of metal together by creating an intermetallic bond. The active element in the process is heat. Heat created and stored in the reservoir of the soldering iron and transferred to the work through the tip. There is to a good soldering tip that meets the eye. First, there is the copper core. Then a plating of iron. Next, a plate of nickel, and finally, a plate of chromium. The solid copper core conducts the heat from the reservoir to the work and is the heart of the tip. The iron plate provides a harder wearing surface, giving the tip a longer life. The nickel plate protects the tip from the corrosive action of the soldering process. The chromium plate makes the metals of the tip immune to the action of the solder. Because of the reactions of air and flux upon the surface of hot metal, oxides form on the tip as it idles and cools. For reliable solder joints, these oxides must be removed. Therefore, the first step in good tip care begins before the soldering starts, while the iron is cold. While the iron is at room temperature, a wire brush can be used to gently remove the scaly oxides from the tinned area of the tip. An abrasive polyurethane foam stick or a 100 grit emery cloth can also be used to effectively remove the oxide. Care must be taken not to damage the protective plating of the tip. The next step is important, whether the tip is new or newly cleaned, and that step is tinning. Applying a protective layer of solder to the exposed metal of the tip. With the iron at room temperature, wrap rosin core solder around the tip and clip the ends. Plug in the iron. Wait for the solder to melt. Wipe off the excess solder and the iron is ready for immediate use. The first step in the actual soldering cycle is wipe the tip on a clean, damp sponge. This is necessary because as the iron idles in the holder, the hot metal of the tip interacts with air and solder to create the troublesome oxides. Make the solder joint. Heat the work with the tip. Melt the solder on the side of the work away from the tip. Re-tin the tip. Just a touch of solder to protect the metal of the tip. Return the iron to the holder. Do not wipe the tip on the sponge before placing the iron back in the holder after completing a solder joint. And keep foreign materials such as epoxies, cements, and coatings from getting on the tip and burning. They foul the tip too. Remember this cycle. Wipe the tip, solder the joint, re-tin the tip, return the iron to the holder. Today's soldering tip is a unique tool designed for specific tasks and requiring special procedures and care. Following the basic procedures of good tip care outlined here will prolong the life of the tip, reduce the amount of solder used, and result in more reliable solder joints. Equally important to the making of reliable solder joints are little-known facts concerning the forming and cutting of component leads before they are soldered onto the circuit board. After thoroughly cleaning the surface of the board and the leads of the component, the correct location on the board must be found and the component aligned with the holes before the leads are formed. The lead can be easily formed or bent with the aid of a pair of round nose pliers. Notice that the lead is bent beyond the 90 degrees necessary to enter a hole in the circuit board. This allows the lead to be bent back to the 90-degree angle and produces a sharp, clean bend that is well within recommended tolerances. The round nose plier is the recommended tool for forming wire leads. The circular jaws are tapered to accommodate wire of various diameters. The taper makes it possible to vary the distance of the wire from the front of the jaws to find a jaw diameter equal to the diameter of the selected wire. This relationship of plier jaw diameter to component lead diameter is important because of the internal stress caused by bends smaller than the wire's own diameter. A wire's own diameter is therefore the smallest bend diameter allowed for a component lead. To reduce internal stress damage to the component during the forming operation, always bend the lead from the side of the plier opposite the component. One last thing to remember about forming. Because of mechanical and heat requirements, the smallest distance allowed between a component and the bend of the lead is 1/16 of an inch. The leads are wiped again to remove any oils transferred from the fingers. A non-metallic spudging tool used for probing, forming, and bending wire leads is employed here to make half clinches on the component leads. The half clinches will hold the component to the board during the soldering operation. The leads are cut before the joints are soldered to reduce possible shock damage to the joint. Here's why. If conventional compression-type cutters are used to cut the leads, the 5 to 10 pounds of pressure exerted on the grips is amplified and dissipated by the jaws. This energy is used to force the wedge-shaped cutting edges into the metal of the wire. By using the law of conservation of energy and analyzing this action, we find that part of the energy created by the 5 to 10 pounds of pressure on the grips is dissipated into the cutting edges, making them dull over a period of time. Part of the energy is dissipated into the component or joint, resulting in possible internal or mechanical damage. And part of the energy is dissipated into the end of the wire, making it a projectile that can fly across the workspace. The recommended cutter for electronic work is the shear type cutter. Using about half the pressure on the grips needed by compression-type cutters and employing a different design, the cutting edges tend to shear the metal with most of the energy directed away from the component. Again, using the law of conservation of energy to analyze the action, we find that part of the energy is dissipated into the cutting edges and in time will dull them. A minimum amount of the energy is dissipated into the component or joint because of the shearing action of the cutting edge. This type of cut has a significantly lower damage potential. A larger part of the energy is dissipated into the wire end, making it a projectile capable of flying across the workspace. As with all the other elements of soldering for electronics, the recommended procedures for forming and cutting are essential for high reliability soldering.